Okay, I think that I can start. Good morning. My name is Massimiliano Guarrasi. I'm an HPC specialist at Cineca, but also an astrophysicist. Here, I want to present to you uh, um, our HPC facility mainly based on an open power system, and I want to show you also some deployment of code we did in the last months on this new architecture. First of all, what is Cineca? Cineca is an inter-university consortium, but also one of the largest HPC facility in Europe. It gives service both for university and Ministry of University Education, and give software solution and service to the university administration, but also information for the ministry, for the management system, and so on. Here I want to show you only the HPC part of Cineca that have as a main aim to the scientific research, and particularly promote the scientific research by the use of the most advanced high-performance computing system in Europe. Apart this, Cineca gives also support for innovation and technology transfer, both for public and private institution, promoting, in this case, the use of big data solution, but also artificial intelligence, scientific visualization, and computer graphics. Cineca was founded more than 50 years ago, and it, for what I remember, was always in the top 500 list of supercomputer, and this is the position of Cineca HPC cluster in the list in the last 10 years. We was in 2012 and position 12 in the list, and with our IBM Blue Jinko system Fermi, and again at position 12 in 2006 with our old Tier-0 cluster Marconi. Currently, I think 5 months ago, we changed our machine, and now we have also another Tier-0 machine that is Marconi 100, that is an IBM power system with, but I will show you the system in the next slide. For now, I want to comment to you that we are at position 9 in the top 500 with our machine, but as Italy, we are the only European nation in the top 10 of the list, and also the only nation with 2 systems in the list, because there is also another system, the HPC 5 system, that was in the list, was managed by the system administrator of Cineca. So currently, Cineca managed 2 of the system of the top 500 list. This is the structure of our infrastructure. Currently, we have 2 Tier-0 system, the old one that is Marconi, that was based on the Skylake and KNL processor, and the newest one that is Marconi 100 that was based on Power9 and Volta GPUs. Apart this, we have other 2 Tier-1 systems that will be replaced in 6 months, I think, that is Galileo and Meucci. All these systems are connected throughout 100 gigabit Ethernet, and thanks to this network, it also a tape library and a disk resource was connected, and Cineca obviously is connected to the internet thanks to a giant GAR network. This is a short overview of our system, because I think that all of you knows what is a Power9 system. Currently, we have a machine with about 1,000 nodes. Each node has 2 IBM Power9 processor with 3 GHz of clock frequency, 256 GB of RAM, and 4 Nvidia V100 GPUs. In total, we have about 350,000 cores, 250,000 GB of RAM, and about 4,000 GPUs. All these cards are connected throughout a dual-realm and Linux ADR InfiniBand network, and currently the sustained link-up performance of the system is about 21 teraflop. It is also possible to receive resources on the system with various methods. First of all, thanks to agreement, you can pay for having the resource. You have to contact Cineca, and your institution have to make an agreement with Cineca for the resources. And for free, thanks to two initiatives. One, it is an European initiative that is praised, and the other one is at the national level, thanks to ISCRA. For what regards praise, the initiative was for all European researchers. That European researcher, I intend a researcher with an European affiliation, and this allocation is for a very large project, as an order of magnitude from 100,000 to 1 million of node hour on our MARCONI 100 system, or it is also possible to require small resources in order to test your code, to port your code on our system, or to improve the performance of your code, obviously. In this case, you have to request to pay a preparatory access. Here in the slide of the presentation, you can find the link for this initiative with all the information you need. Furthermore, if you are an Italian researcher, you can request a more moderate amount of resources from 1,000 to 50,000 node hour, thanks to the ISCRA initiative. And again, here you can find the link to find all the information you need to submit the proposal. And that's it for the part of the presentation that regards Cineca infrastructure. Now I want to show you 3 examples of porting of code on our system, done with 3 different methods. And I want to show you both the method, especially for what concerned the first code, but also the results we obtained. First of all, the first example is about the stream code. The stream code was developed by the CFD Sapienza group that is led by Professor Pirozzoli and Professor Bernardini, and Cineca contribute to the development of this software thanks to our colleague Francesco Salvatore. The code is a classical DNS code for compressible fluid flow. It solves the Navier-Stokes equation with a discretized grid, discretized Cartesian grid, and it uses also a 3-stage tiered order Runge-Kutta scheme that is quite standard in this field. And The original code was developed to run on classical GPU system or and was also optimized for kernel. Now we ported it on a multi-GPU system. To do this, the cost in terms of person months of the operation is about 60 person month, 8 for the first porting and 8 for the optimization. In order to choose the best approach for the code, we have various solutions. We can choose to use an approach with MPI plus OpenMP or OpenSCC approach, and this is the simpler approach that uses directive. The second approach, possible approach, is using CUDA, and the third one is using more exotic language like OpenCL or similar. In our case, we choose to use CUDA Fortran, and inside to CUDA Fortran, we choose to use the CAF kernels that allow us to use directive inside CUDA. And as you can see from this example on the right bottom, it is quite simple to move a do loop into GPU simply using CUDA kernel, simply by adding one row at the beginning and another row at the end. Clearly, not all the code can be used, can be ported simply with this command. You have, in any case, to use other instruction, and in this case, we use some processor instruction in order to switch between the standard version of the code and the CUDA version of the code, because we want to have the same code both for GPU and GPU. And simply by switching the definition of a system variable, in this case use CUDA, we can switch between GPU and CPU. In this case, we can define GPU specific variable. You see that was enabled only if use CUDA is defined. We can, with the same method, we can allocate this variable, and at the end, using a slightly more complicated instruction, if def, else, and if, we can select the right instruction for the GPU code or for the CPU code. Using this method, we complete the first CUDA version of the code, and starting from this, we proceed with the optimization of the code, following quite standard best practice. First of all, we start with a baseline code, CUDA code, then we change the memory layout to adapt it to the structure of CUDA core. After this, we change the transposition of matrices to improve the performance of the code. Then we pre-compute some primitive variable to reduce the number of access to the main memory of the node. And finally, we readjusted the memory layout also for MPI buffer. Here we can see the results of this optimization. In the first row, you see the start in red, the start execution time of the code, and the in the third column, you can see that the time of execution increase after the changing of the layout, and this is quite common, but the changing of the layout of memory, it is necessary in order to proceed with the following optimization step. And as you can see in all the next step, the time to solution will strongly reduced, and at the end, the final time to solution is less than 1/2 of the original time. It is also possible to boost further the performance of the code using remote direct memory access for read and write, but it is possible only in some machine. In our case on Power9 it is possible, but not in all the machine it is possible, since it depends from the version of MPI you are using. And final, this is the results obtained comparing the time to solution on different systems. As you can see on Broadwell, we have the first column results. We use 2.9 seconds. Then we have the results on a single K40 GPU, then on a P100 GPU, then the next one is on Skylake node, and finally on a V100 GPU. As you can see, the boost of performance passing from a standard Broadwell node to a single GPU, it is enormous. If you consider that in a single Power9, IBM Power9 node, you have 4 V100 GPU. If you have an out grid point, you can see that the boost of performance is really high. Here I report, but I have to be fast because we have time. You can see the weak and strong scaling, and also here you see that the performance are very good, up to some thousand of GPUs, and also the strong scaling is good here, up to 8 GPUs, but only because the number of grid points is very low. Increasing the number of points, you can increase also the scalability to 1000 GPUs easily. And that's it from the first code. As a second code, I want to show you the work done by the CEISSOL Center of Excellence, and Cineca is part of this Center of Excellence to port the SEISSOL code on GPU. CEISSOL is a Center of Excellence code that have as aim the area of solid earth, and to port and improve the performance of solid earth codes to be ready for the exascale era. In this framework, 10 flagship code was chosen, and the SEISSOL code was one of these flagship code. It was developed at Technical University of Munich, and it solved large-scale simulation for seismic wake and earthquake dynamics. It was based on discontinuous Galerkin method, and it also implements a local time stepping procedure in order to speed up the time integration process. Some of the most important HPC main feature of the code is the YATETO domain-specific language that was developed for this code. It is machine independent. It is based on MPI plus OpenMP, and the parallelism is based on BLAS-like libraries. In order to port this code on GPU, we have to give a new structure to the code, and particularly we pass from the developer and our Cineca collaborator pass from MPI plus OpenMP to MPI plus CUDA. To do this, we pass from single to batch at gem computing, and at the same time we generate both code for CPU and GPU, and we also develop a new module for Yateto library. These are the results of the benchmark on the gem part of the library, because we compare the performance of the standard cuBLAS library with the gem inside the Yateto library, and as you can see, in the left part of the screen, the performance of the GemForge library was always better than the standard cuBLAS library, both for single and double precision. Another important thing we can see is comparing the performance of the entire code passing from a standard Xeon system to an Nvidia system, and changing the number of elements and the number of, the number of grid points. As you can see, for high number of elements, the use of GPU is better. The performance are higher than a standard CPU system. And the drop down for a small number of points is due probably to the major cost of the communication in case of small packages. And finally, we want also to test the code on a real system, and here you can see the strong and weak scaling of the code, changing the number of grid points. In this case, we reached 0.5 single precision petaflop using only 64 nodes of our machine, and in any case, this scalability is quite perfect. We want to show you also the scalability of the code using the local time stack procedure that is still not complete, and since it is highly unbalanced, as you can see from the left side figure, the performance are not perfect, but in any case we have a gain of time to solution performance, since in this case the time to solution is slightly less than the global time step case. Passing to the last one, code, I have, I think, 3 minutes, more or less. I want to show you another code that is developed by the Tor Vergata group of Sauro Succi and Giacomo Falcucci, with the help of our colleague Giorgio Amati. And this code is a quite standard lattice Boltzmann code, and that was written in Fortran, that support multi-block. The parallel paradigm is used, is MPI or MPI plus OpenMP, and now also MPI plus OpenSCC. So in this case, we are developing a code using not CUDA, but directly OpenSCC directives. We we want to try to keep performance portability also in the porting. And here I don't want to show you the code, but simply an example of the performance reached of a code that is right now in production. The case we want to show you is the EU Plectella aspergillum, that is a sponge that live in the sea, and that was quite interesting from the computational fluid dynamics point of view, since it modified the flux since that is inside the sponge itself. The simulation that we perform use about 50 billions of grid points, 7 terabytes of RAM, and use about 5 days of simulation using 500 GPUs on our system. We test various systems. We use a brute force approach, and as you can see from the speed weak scaling speed up, we have more or less the same and quasi-ideal speed up. The performance using 1000 GPU is the parallel efficiency is about 73% of the total ideal performance, and this is very good. And to finish the presentation, I want to show you the flux using different grid meshes to model the sponge, and that's it. If you have some question, now I'm trying to block the presentation, and now I try to see also your comment, but I didn't see any comment by now. Okay, no comment. Since there is no comment, I want to stress the fact that we choose as an example 3 CFD code, but the codes are interesting from the scientific point of view. Both will be used in production, and the approaches we use are different from the 3 code. In the first one, we used a CUF directive procedure. In the second one, we use directly CUDA Fortran, and in the third one, we use OpenACC. In any case, both the method used to perform to do the porting reached their scopes. That is, boost the performance of the code of at least a factor 4, but in many cases more than this. And it is not so difficult to do, because the effort for a production code can be high, but for a smaller code, it requires only a few months of work of a single person. So I think that it is a very good and fast approach to do this. Apart this, I want to stress also the fact that on power system, the performance of this code are even better, because the use of the dedicated NVLink network boosts the performance and the communication between the memory, the main memory, and the GPU memory. And that's it. I think that we have 2 minutes to the end, so therefore this is the moment to ask a question. If not, I thank you for attending the meeting, and thank you also to the staff of not yet. I see now a question. It uses intrinsic code for Power9. Not yet, but probably in the future, in order to better optimize for our machine, probably some Power9 instruction will be inserted. And that's it. Thank you again to the organizer and to the attenders. And goodbye.